Hey there, organic students. In this video, I want to talk a little bit more about molecules with multiple stereocenters. This molecule I'm showing you here does not have multiple stereocenters. It only has one stereocenter. But I want to point out a trick to you before we go on. If I give you a molecule that has a stereocenter and I ask you to generate its enantiomer, there are a couple of different ways that you can do this. In this example, I can simply change the orientation of the hydroxyl group from pointing away from you to pointing towards you. But I want to point out to you that in doing so, what I've really done is I've switched two groups attached to the tetrahedral stereocenter. So whenever you want to draw an enantiomer of a chiral molecule, all you have to do is switch two groups attached to the tetrahedral stereocenter, and you will generate the enantiomer. Another way that you can think about drawing enantiomers is to imagine that you are reflecting the original molecule through a mirror, and that reflection will be the enantiomer. Again, I want to point out to you that essentially what we have done is switched these two groups to generate the new enantiomer. Now let's have a look at molecules with multiple stereocenters. And let's start with 3-bromo-2-pentanol. Hopefully at this point you're able to identify the two stereocenters in this molecule. And we can start to draw different stereoisomers. You can start with any one of the stereoisomers at random. We can calculate the number of possible stereoisomers using our formula, 2 to the n, where n is the number of stereocenters. This gives us a maximum number of 4. This is our first stereoisomer, and this is a representation that you have not seen before. You can think of these groups on the top as being sort of like a tulip, with the vertical bond as the stem, and the other bonds being the petals. You can think of this group on the bottom as being sort of like a tripod. If you can't imagine this, or you can't really get a good mental image of this, stop the video now and build a model. We can reflect through a mirror and generate the mirror image of this molecule. Now, I want to point out to you again that in going from the first representation to the second representation, what I've essentially done is switched these two groups, and I've switched these two groups, and that gives me my new stereoisomer. The configuration of my stereocenters on the left are R and S, so the mirror image must have the S and R configuration. Now you know that I must have two additional stereoisomers, and one way that I can generate a new stereoisomer is by changing only one of the stereocenters. So if I change the stereocenter on the top, or just switch two groups, but keep the stereocenter on the bottom the same, this will give me now the SS isomer. If I reflect through a mirror, that is going to give me the RR isomer. These two isomers are a pair of enantiomers. These two isomers are also a pair of enantiomers. This is a pair of diastereomers, stereoisomers that are not mirror images, and this is a pair of diastereomers as well. These two are diastereomers, and these two are diastereomers. We do indeed have 4 stereoisomers of 3-bromo-2-pentanol. Let's look at 2,3-dibromobutane now. Hopefully you can recognize that we have 2 stereocenters in this molecule, so the maximum number of stereoisomers that we could have would be 2 to the 2, or 4. We can start with any one of our stereoisomers at random, reflect it through a mirror to get its mirror image. Now we have the RS and the SR, and I'm going to change just the stereocenter on the top. That will give me the SS isomer. If I reflect that through a mirror, that reflection will be the RR isomer. I want to point out to you that these structures that you are looking at represent only 3 stereoisomers, not 4 stereoisomers. It may not be immediately obvious to you that there is a plane of symmetry in 2,3-dibromobutane. Remember that I can rotate freely around a single bond, and if I rotate around this bond in the center, that will give me a new representation, and in this representation you can see immediately that we do have a plane of symmetry, or a mirror plane. If I take the isomer in the upper right and I rotate it 180 degrees, see that I'm starting with the S on top and the R on the bottom. That's going to put the R on the top and the S on the bottom. Now, I can superimpose these two images. So that means that my first two structures were identical. 2,3-dibromobutane has only 3 stereoisomers. And that's because one pair of mirror images will be superimposable. See if you can pick out the meso compounds from these molecules here. Go ahead and pause. And remember that a meso compound has multiple stereocenters, but it also has a plane of symmetry. These are the meso compounds. So how did you do?